Thank you very much. Thank you for the opportunity to give a talk today. So I will talk about some questions related to case stability, and I will consider some special class of Fano pairs. So I will define them first, and then I will state the main result, and then I will talk about case stability. So this is the plan. So let us consider the pair x delta, which is log smooth and log Fano, such that delta is a non-zero divisor, which is integral and reduced. Let me comment on the assumptions. So log smooth means that x is smooth, and delta is a simple normal crossing divisor. And log Fano means that minus kx minus delta is ample. We also assume that this divisor delta, which is called the boundary divisor, is non-zero, since otherwise we get the classical Fano variety, which is well known, and the case stability problem for Fano varieties is studied by other people, including Ivan Chiltsov and many more. So I will concentrate on the case where delta is a non-zero divisor. Yes, sure, smooth and project. Yeah, thank you. All right, so such varieties X, which admit the structure of log smooth, log Fano pairs, they very much resemble the classical Fano varieties. So it is well known that in this case, X is rationally connected, and they don't have cohomology of the structure sheaf. And so they share many properties similar to the properties of Fano varieties. So the Mori cone is polyhedral, and they behave well with respect to the Mori theory. Let me give a couple of examples. So just as in the case of classical Fano varieties, such pairs are understood in dimensions up to 3. And if dimension of x is equal to 1, there is only one such pair, namely P1 with a point. If dimension is equal to 2, then such varieties X are not bounded. So recall that classical Fano varieties, for example, smooth Fano varieties are bounded, which means that they belong to finitely many deformation classes. But in this case, we can have such pairs where Fn is the Hirzebruch surface and S is a section of the structure morphism with self-intersection minus n. So we have infinitely many pairwise non-isomorphic varieties. In dimension 3,
besides this, there are probably some other.
yes, sure. Sorry?
You can add fiber.
Yes, sure, sure. This is not the classification. This is just an example, yes, of an infinite family. And as for the classification, there exists. Yeah. No, we, as you said, we also can have this pair. So the variety itself is the same, but the boundary is different. In dimension 3, there exists a classification. Not quite. We also can have P2 with a line.
But this is not an infinite series.
As for infinite series, yes. Yes, we only can have two such series, right? Yes. As for the classification,
And for all others, the underlying variety is also different. Is it correct?
yes, the underlying variety is either P2 or a Hirzebruch surface.
No. Okay.
Is also Hirzebruch surface.
Ah.
There exists a classification due to Hironobu Maeda, which is obtained in '86. And this classification is rather large, so there are many infinite series. And actually, his classification does not contain information on how to distinguish such series. It is rather hard to work with his classification. So later in my talk, I will explain how to clarify to clarify his classification, how to make it a bit more precise. Yeah. One more remark on the structure of such pairs. In fact, one can bound the number of components of the boundary. So if X delta is a log-smooth log-Fano pair in this sense, then if we write that delta is equal to the sum di, then one can show that n is bounded by the dimension of X, and if this bound is attained, then one can describe the geometry of such a pair rather explicitly, namely, in this case, this pair is toric, which means that X is a toric variety. So there exists a structure of a toric variety on X such that the boundary divisor is torus invariant. So this is a theorem proven by Joaquin Moraga and myself. All right. Now let me.
And what about the converse? Not in toric variety. It's log-Fano, right?
I mean, this bound is not necessarily obtained for toric varieties, for toric pairs. For example, we can have P2 and the line, and this pair is toric, but the bound for the number of components is not obtained in this.
No, I'm asking which of toric varieties are log-Fano?
We don't have result on this, so I think some result can be obtained in this direction. Maybe not very hard, some combinatorial description. Okay, so at least some toric varieties are log-Fano, but we don't know exactly which, and this is a nice problem actually. Okay. Now let me formulate the main definition of today's talk, which is due to Kento Fujita. And this definition is related to the work of Maeda. So consider a pair XD such that this pair is say log-smooth and log-Fano. But now D may have arbitrary coefficients between 0 and 1. So one can say that we consider KLT log-Fano pair, which means that this coefficient is less than 1. And we also assume that X is smooth and the support of D has simple normal crossings. Okay? Then we say, yeah?
Even including the components which come with coefficient
There is no use to consider the components with coefficient 0, so we can assume this.
No, but I mean the simple normal crossing assumption gives you something in this case. Yeah?
For coefficient 0?
Constraint.
Yeah, but there is no use to consider such components. Yes, then we say that such a pair is a log-Fano pair of Maeda type if there exists a divisor delta, integral and reduced, so some dg, such that the support of d is contained in the support of delta, and x delta and is log smooth and log Fano. So let us also assume that this boundary is non-zero. Again, otherwise we get the classical Fano variety. Okay, so roughly speaking, log Fano pair of Maeda type is the following thing. We start with the pair in this sense, and then we vary the coefficients of this pair such that we obtain a KLT log Fano pair. Okay, so this definition is just the way to make a KLT log Fano pair starting from log smooth log Fano pair in this sense. Okay, why this definition is important? Why does it make sense? Because the theory of K stability it works with KLT pairs essentially. All right.
And what about these two series in dimension 2? Which of them have this problem? I mean, for which of them such a variation is possible?
Yeah, we can add some coefficients, for example, here. So here it is clear that we can add arbitrary coefficient. But here we may have some constraints on these coefficients, and for some values of the coefficients we will have a log Fano pair, while for the other we don't have such condition. And actually these values of coefficients are called in some works body of ample angles. So in the works of Yanir Rubinstein and maybe Ivan Chiltsov, but I'm not sure. So people study such coefficients, such values. Yeah, so not for all values we have log Fano pair. Thank you for this question.
So basically, Maeda type means that you have a pair which is like a fractional divisor, and you require, which is log Fano, and you require it's still log Fano when you round up all the coefficients.
Yes.
To integral ones.
Yes.
And maybe also add some extra components, or you're not?
Yeah, this is a good point. So, for example, this is not quite a round up because we can have coefficient 0, right? And then the round up still will be 0.
So you're allowed to add even more
Yes,
components?
yes. We round up, and we can add some more components. Yeah.
So for instance, Fn and 1/2 of F is of Maeda type, correct?
I'm not sure. I think we should have some coefficient for the section as well. Because if you add just some fraction of the fiber, it will not be log Fano as far as I
If you are
can
allowed
see.
to add extra components, then just add
No. The pair itself, xd, also should be log Fano. I think your pair is not. So in the case of Hersey-Brooks surface, we should have at least some fraction of the section. Yeah, so this is a bit tricky, as you see. Okay. Now I can formulate the main result. So theorem. In this result, I will use the word k stable. So I have not defined what it is, but let me first state the result, and then later I will give some definitions on k stability. But first, the main result. So assume that xz is log Fano pair of Maeda type with dimension of x, where dimension of x is equal to 3. Okay? So then assume further that D is reducible. I will comment on this assumption. Then this pair xd is k unstable with a finite number of exceptions. Moreover, these exceptions can be explicitly described. So we can describe completely the threefold x, the boundary D, and the value of coefficients by the components of this boundary. So we have all information, and we know that for these exceptions, the corresponding pairs are k semi-stable, and with some further conditions on the coefficient, this pair is k polystable. So I will explain further what does it mean, but still, now I give the result in the most crude way, in the most crude form. Okay. Yeah. So what is interesting here is that although we have
and what about dimension 2?
yes, in the dimension 2, similar result was obtained by Kenta Fujita. Maybe let me formulate it now. So I planned to formulate it later, but now maybe for the context, it makes sense to formulate it. So if xd is a pair of Maeda type and dimension of x is equal to 2, then this pair is k semi-stable and respectively k polystable, whatever this means, if and only if we have either P2 with a conic or a quadric with a line of type, with a curve of type 1, 1. So here C is a conic. Yes, smooth conic, and the coefficient is less or equal than 3/4, respectively, strictly less. And here the curve C has type by degree 1, 1, and the coefficient is less or equal than 1/2, respectively, strictly less than 1/2. So this is the result in dimension 2 for k semi-stability and k polystability, which is stronger than k semi-stability, and we have and Fujita has precise description for such pairs. So I have similar description in dimension 3, although it is larger, and it is maybe it doesn't make sense to write it down at this moment, but at the end of my talk, I hope to write it down. Okay? All right. So
in dimension 2, the underlying chloride is delta.
yes.
And what about your theorem?
In my, let me think. Yeah, this is a good question. Yes, in my list we also have Fano. Yes, the center lang is Fano. Yeah. Yeah. Okay. Now let me say a couple of words on the classification of such pairs. So how to obtain such a classification. Classification of log-smooth log-Fano pairs, x delta. In dimension 3, yes. So the first step to do such a classification. So I will explain my approach to this classification, which is of course based on the works of Maeda, Casagrande, and Fujita. And this approach is quite natural. So it uses the minimal model program, some special form of the minimal model program, and we should start with the following observation: that there exists a one complement gamma for the pair x delta, which means that gamma is some effective divisor such that kx plus delta plus gamma is linearly equivalent to 0. So delta is an integral divisor, and the pair x delta plus gamma has good singularities, namely it has log canonical singularities. Then the second step is to show that there exists. So we can.
What does it mean here? Is it is simple non-crossing divisor? Because x is smooth here in case.
So I expect that this is the case, but I don't need this. So for me, just log canonical is enough. But in fact, yeah, maybe it is log smooth, but to prove that such a complement is log smooth is harder than to show that it's log canonical. So essentially, how this one complement is constructed, we constructed it inductively on the boundary delta and then lift it to the x, to x. Then the second observation is that we can run a kx minimal model program with scaling on gamma, which is equivalent to minus kx minus delta. So essentially, the crucial observation here is that such pairs, they admit a canonical polarization. Namely, by definition, the divisor minus k minus delta is ample. So we can run minimal model program with scaling on this divisor. And also, it is easy to prove that this minimal model program is also a minus delta minimal model program and minus gamma minimal model program. Essentially, this means that we contract the extremal. So at this step, we contract extremal curves which are negative with respect to these guys. Okay. Then in dimension 3, so these arguments work in arbitrary dimension. But what is special to dimension 3 is the following. If dimension of x is equal to 3, then each step is a contraction of P1 to a smooth point to a smooth point to P2, sorry, P2, I'm sorry, to a smooth point, and the result of the minimal model program is a Mori fiber space. Okay. Finally, if the boundary delta is reducible, then using result of Fujita, we know that the restriction map from the Picard of X to Picard group of reducible variety delta is injective, and consequently the Picard number of X is less or equal than 3. So how this can be proven? Well, we know the classification of such pairs in dimension 2. We know how they can be glued. And then we know what we can have for Picard of delta. And since this is an injection, we get this. So in fact,
The boundary is itself, every component of the boundary is also a log Fano?
yes, sure. And this is,
Just by junction?
yes, of course. Yes, by junction, we can work inductively with such pairs. So what is good about such pairs is that we can work inductively. We know that each component of the boundary delta is log Fano. And if we know the classification in lower dimensions, we can say something about in
I'm sorry, Kostya, can you explain the case about dimension 3? It says in dimension 3, then that is...
Yes, here we use the classification of extremal contractions in that dimension 3 due to Mori. And we can say that on each step we have the simplest possible birational contraction, which is a contraction of a plane to a smooth point. So it is the reverse operation, the converse operation to the blow up of a smooth point. Huh?
Известный алгебраический.
So using this approach, we can state the following proposition. Sorry, one more remark. This minimal model program is called special minimal model program in the works of Casagrande, Cynthia Casagrande, and Kento Fujita. Yes, and using this approach, we can state the classification. We can formulate the classification. So if X delta is log smooth log Fano of dimension 3, then there are the following possibilities. So sorry, if delta is reducible. So of course one can use this approach to classify all such pairs, but I work with the case of reducible boundary. So then there are the following possibilities. So either X is Fano with the Picard number 1 and index 3 or more. So in this case, we have either P3 or a quadric in P4, smooth quadric in P4. Or X admits an extremal P2 bundle structure over P1. And such bundles can be explicitly described. So there are several infinite series in this case. So I will not write them down. Probably I will show you the table at the end of the talk.
That's the end of Fn.
Huh?
That's the end of the Fn
yes, this is one of the analogs of third possibility is that we have a quadric bundle structure over P1. Then we can have P1 bundle.
When you say quadric bundle, you mean that quadric bundle?
Yes, so all the fibers are either P1 times P1 or a cone over a conic. Yes, or we have P1 bundle over log del Pezzo surface, that is log Fano pair of the dimension 2, so over P2 for Fn, and also they can be explicitly described. The next possibility is that we have a blow up.
But a P1 bundle over Fn is a quadric bundle over P1.
Here I assume that all the structures are extremal. So this is not quite the same thing.
Relative number is 1.
Yes, yes. Then we have blow up of P2 bundle over P1 in one point. And again, this P2 bundle has some special form which can be explicitly described. And the last possibility is that we have a blow up of a quadric in a point.
So, and which of the series, so you have 1 and 6, which are obviously sporadic, and between 2 and 5, which of them actually form infinite series?
All of them form infinite series. And in the case 2 and 4, we have several infinite series. Okay. Yes. What is nice about this approach is that for each such a pair, we can associate an invariant, namely the type of this contraction is invariant for the pair, because this minimal model program is canonical. It depends on X and the divisor delta. And hence, this procedure is canonical, and it gives us some invariance.
So each time you have just one extreme array.
This is a subtle point. So it, to be precise, it is almost canonical, because sometimes, but very rare, we have several possibilities. We have several possibilities to contract array. We can have.
But you mean that the terminal final point is doesn't depend on the choice, right? What do you mean? But by
So.
I don't understand.
Yeah.
A posteriori, you just have one contraction of a plane at most, right?
Yes, that's
When you look at
correct.
this composition, then
Yes, that's correct. But
there is no choice.
what I mean is that priori we can have.
We start with variety with maybe big Picard number, and we run this MMP, and we get more fiber space, but possibly we can run MMP in another direction.
Yes, that's
and
correct.
In principle, we can get another.
So let me state the precise thing. So almost always we have a unique way to get to one of such cases, because almost always this MMP gives you just one possibility to contract an extremal race. But sometimes you can have some freedom. You can have, so for example, if you have P1 and P2, you can either get this case or you can get this case. But such cases are very rare. And almost always there is a canonical way of getting there.
Yeah, but this is not the question of running MMP because this is already the end point of MMP. You just interpret it differently as a P2 vibration or as a P1 vibration.
Yes, that's correct. But the problem is starting from such a pair to classify it, to get a list of mutually excluding cases. And to this aim, it is helpful to have some invariant. Okay. Yes, now I will talk about case stability. So I will briefly recall the main definitions. Now we will assume that xd is a KLT log Fano pair. For example, xd can be a log Fano pair of Maeda type. Then I will define so-called beta invariant. So essentially, case stability was defined in terms of test configurations, but then it was reformulated by Fujita and Lee, right? Fujita and Lee in the language of beta invariants, which I shall use. So assume that E is a divisor over X, which means that there exists a birational morphism from Y to X and E as a divisor on Y. Then, by definition, beta invariant of E with respect to the pair xd is a difference of two numbers, A xd of E and S xd of E, where in turn A is a number called log discrepancy, and S is called expected vanishing order. So recall that the log discrepancy is just the following number. It's just 1 plus the coefficient of E in the divisor ky minus f star of kx plus d. And the expected vanishing order, it is defined in the following way. So let me introduce the following notation.
So do you assume that Y is small or something?
No.
Just discrete variation.
But without any assumption, is it correct that this definition is independent of the choice of a model?
Yes. Yes, because if you have two you just make a...
That's not generic point of E. Y is smooth in a generic point of E. This is not.
If you have two models, you make a further model. And yeah, so then you have a volume of L, and then the integral from 0 to infinity of the volume of f star L minus TE dt. This integral is in fact finite, so you just compute it up to pseudo-effective threshold. And volume, so I hope there is no need to define the volume of the divisor, right? Yes, so this number is called expected vanishing order. So then we're ready to formulate the definition of a k-stable pair. So it computes the asymptotic of the growth of this divisor, which somehow reflects the order of vanishing along E, as far as I understand. Maybe of this guy.
This is just coefficient. Looks like roughly speaking, it's just coefficient. So E is asymptotic.
Okay. Now, following definition. So xd is k is divisorially semi-stable if this number is greater or equal than 0 for any e on x. Respectively, it is divisorially stable.
On X, not over.
Right. Here we have divisorial stability. Respectively stable if here we have strict inequality. It is called K semi-stable, respectively K stable if this invariant is greater or equal than 0 for any e over x, respectively cyclic. Okay, and one more thing. So I will not give the definition of polystability, but I will just say that there is such a notion of K polystable pairs, which is weaker than K stable, but stronger than K semi-stable. And what is important that for smooth, for example, for smooth Fano varieties, K polystability is equivalent to the existence of Keller-Einstein metric, which is important from the point of view of differential geometry. Okay.
In this case, you don't need X to be fun, right?
Yes, sure. This is just a KLT log.
Like minus K plus DPD should be somehow.
Minus K minus D should be ample.
Ample.
Yes, yes. So,
At least big.
yeah, maybe. But in my assumption, this is a log Fano pair, so minus K minus D is ample. Okay, so now let me explain how to work with, how to determine whether a given log Fano pair of Maeda type is K semi-stable or K polystable. So I'll start with a result of Fujita. Which is also proven by Rubinstein and Chiltsov in slightly different setting of asymptotically log Fano pairs. So if xd is log Fano pair of Maeda type, then or even more generally, so let me state it like this, sorry. So if this pair is log smooth and minus kx minus 1 minus beta d is ample for all small values of d, then this pair is not K semistable. Not K semistable. Again, for all small values of beta. So this result says that if the coefficients of the pair are close enough to 1, then we don't have K semistability. So this shows that the really interesting case is to analyze the coefficients that are bounded somehow from 1.
So here D is not assumed to be reduced.
Here, yes, let me say it like this.
And you multiply all the components with the same number.
Yes, yes. Yes, but in my result, I analyze K stability for any possible values of coefficients.
I don't understand. If X is just Fano,
Yes.
and take D is, for example, anti-canonical, general anti-canonical element, then everything is works, like, right?
Yes.
So it means that any Fano is not K semistable.
This pair. So this is K semistability for pairs.
For pair.
For pairs.
Yes.
Yes, it says that if the coefficient of this anti-canonical is close to 1,
For very small.
if the coefficient of this anti-canonical is sufficiently close to 1, then yes, this pair is not semistable. So all this business is a generalization of K stability for pairs. So I don't say anything here. Okay. Then how can we check K stability and K polystability? Essentially, my approach is based on two results. First one is due to Jean, which says that we can use the symmetries of a pair, namely if G is a
Juan is going to be here in an hour, right?
I hope so. Oops. Sorry.
Can I ask a question?
Yes, sure.
So, in this theorem, I think, maybe I'm wrong, but I think maybe you missed some condition. So, you condition that minus k minus 1 minus beta d ample, it basically means it's asymptotically log fun. Yeah?
Yes, you're right. So this is a particular case. Yes.
I think for Jetta theorem, basically you need to assume that minus k minus d is big, yeah?
No, I don't. I'm not sure because
Wait, but this means it's not k semistable
for all small betas, I'm not sure that he needs the bigness condition, because this is just a very simple observation. It follows basically from definition of beta invariant. I don't, as far as I, maybe I'm wrong, but as far as I...
Wait. Let's just take a case, D is element at minus k.
Right.
Then this condition, or first condition automatically satisfied.
Yes.
But in this, so beta is small, it means minus k minus 1 minus beta d is very close to 0, yeah?
Right. And minus k minus d in your case is 0. So it is not big. But I think the result is...
In this case, it's actually k semistable.
Why? No, you're saying that minus k minus d is semistable, or what? This doesn't make sense. This doesn't make sense because I defined k semistability for log Fano for log Fano pairs. I mean,
No, I'm saying that not minus k minus d, but minus k minus approximately d with coefficient approximately 1.
it is not. It is not semi-stable. In this case, I think it is not semi-stable.
And how can we see it in some simple way that it is not?
I mean, I don't have time to give the proof, but
Okay.
Okay, can we take some particular Fano, for instance?
yeah,
Like-
maybe.
Maybe I'm wrong. Question.
Yes.
I think you need condition minus k minus d is big.
Why? Do you have a counterexample?
Because without this it's not true.
And who is the counterexample?
Almost more or less everything else. Okay, let's don't focus on this. So let's not focus.
Okay, maybe if you come up with a counterexample, then we can discuss.
No, everything. Take P3 and elliptic curve. Cubic curve. P2 in the cubic curve.
Mm,
P is the cubic curve, X is P2.
and you're saying that it is case semi-stable for small values of beta?
I think it's case yourself for all values between 0 and 1.
Okay, maybe let us check this after my talk because I have only 10 minutes left, okay?
One numerical condition. I think minus k minus d should be when big.
Yeah, I'm not sure. Okay, let's discuss it later. Okay, so I don't have much time, so I just say that if we have a group acting on the pair, so G is an algebraic group, then to check semi-stability, we only need to check divisors which are G invariant. So if is greater or equal for G invariant E, and respectively if G is reductive and we have strict inequality, then this pair XD is K semi-stable, respectively K polystable. So, well, let me comment on how, using this classification, we can decide whether a given pair is K semi-stable or not. Well, we can try natural candidates, namely divisors on X. For example, the components of the boundary delta, and usually one of the components of the boundary destabilizes the pair. So we compute beta for this component. Usually it is negative, so in almost all cases. For some cases, we also have to compute beta invariance for different divisors, which are not the components of the boundary, and we still get a negative number. So this is rather easy, but to prove K semi-stability, we need some theory, for example, this result, and we need the group action. The second tool to check K stability is the following result of.
When you say that a divisor is G invariant, if this is a divisor over X,
This means that we have a morphism which is G equivariant, and yeah.
so the model is defined.
Yeah, sure. Yes, yeah, of course. Theorem of Chiltsov and 8 co-authors, including Fujita and many more. So it says that if, so this result is based on his work, but I adopted it to my setting. So it says that if XD is a three-dimensional log Fano pair of Maeda type with the additional condition that the cone of movable divisors is equal to the Neff cone. This condition is satisfied for example, for Mori dream spaces, but not for all log smooth log Fano pairs, not for all such pairs. So this is an additional condition. And assume we have a flag of subvarieties where z is a curve and y is a surface. And assume that we have a divisor E over X such that the center of E on X is a curve Z. Then we can explicitly bound this ratio of A over S. It can be explicitly bounded by the following two numbers. The first one is the ratio for Y. And the second number is the inductive, the number defined on Y using adjunction and some number S, which I denote like this. And there is an explicit description of this number using some integrals and some functions on of the divisor Y and E.
This equality, is it condition or conclusion?
So the conclusion is this. Then for any E.
Before this is assumption.
Yes, so this is an assumption. So if we have.
Is it not automatic?
No. No, as far as I understand, this is not automatic.
And what is dy?
Sorry, this is not automatic because such pairs can admit small contractions.
Basically means no flow.
Yes, and there are
It's
some.
automatic.
Yes, for Fano this is right, but for log Fano there are some. There is a difference between these two cones. So, but for the all cases that are interesting for me, this holds. And in the remaining minute, let me describe the list. So, using these two approaches and using the classification that I have described, so I do case-by-case study, which divisors destabilize things, and in the remaining cases I check K semistability and K polystability.
Question, maybe in Maeda case it's always.
No. There are small contractions sometimes. So this is not automatic. So finally, the list. So I will tell you just very briefly the cases. There are 5 of them. So the first case is P3, and the components are a plane and a quadric. And also, in each case, I have precise values of coefficients for which it is K semistable and for which it is K polystable. Then we have a quadric in P4, and we have 2 hyperplane sections. Finally, we have, sorry, not finally, then we have P1 times P2, where D1 is equivalent H plus F, and D2 is equivalent to F, where F is a fiber of the contraction to P1, and H is a preimage of a line on P2. Then we have blow up of a quadric in a plane conic. The first divisor, the first component is the exceptional divisor of this blow up. And the second component is a strict preimage of hyperplane that contains a conic. Right. Right. It's a section, yes. And finally, we have divisor of b degree 1, 1 in P2 cross P2, and D1 is divisor of b degree 1, 0, T2 is divisor of b degree 0, 1. So, yes, I also have the picture of the values of coefficients for which the pair is case semi-stable. And just as in the two-dimensional case of Fujita, if we have strict inequalities for the coefficients, then the pair is K polystable. So we prove it using the theorem of Zhang, the G invariant approach. Okay, so
Why can't we have P3 with 3 planes?
Because this pair can be destabilized. So this is shown. So this is just the computation, and actually the computation for hyperplane arrangement in any dimension was made by Fujita.
And who destabilizes it?
I think one of the planes should. So usually destabilizing. So usually you have a component of the boundaries that destabilizes things. Okay, so I guess this is it. Thank you for your attention, and let me stop here.
So we already have a question in chat. So Vanya sent us a link to Kento's paper, and Kento indeed
Bigness assumption.
requires bigness, but also surprisingly he also requires irreducibility assumption. From D.
Yeah, maybe. Yeah, maybe. So, sorry, then I was not accurate. Yeah, but irreducibility is a strong assumption. So, but using the classification, we can see that indeed in all the cases, if the coefficients are close to 1, then we have not case semi-stable pair. Yeah, so this is a more general.
Question, but I think you assume everywhere that it's Maeda type. So
Yes, of course. In my work, yes, of course. In my work, this is it. Yes, you're right.
So, in your theorem, you assume that the boundary is reducible. And what if it is irreducible?
Yes, so then I expect that still we have only finitely many case semi-stable pairs. Of course, it is needed to be checked. And the problem is that this classification is large. And as far as I can see, there is no approach to avoid classification to prove it. So maybe there is, but I don't know such approach. So yes, this can be done, but what is interesting about the case of reducible boundary is that we can have some conditions for coefficients. So this is some convex body which we can explicitly describe.
Any other questions or comments?
So you consider this is just case by case analysis, right?
So as I described, there are several series, 6 if I'm not mistaken, and actually we can consider these 6 cases, and usually the same approach works in each case. So there's a table, and there is no need to consider all the series. So usually we can just concentrate on these 6 cases and apply some arguments in these cases.
How about toric case? Is it simpler?
Yeah, there is a method for computing beta invariant for toric varieties, but I don't use them. Maybe it is indeed simpler, but of course not all such pairs are toric. So this is the problem.
I see, but still you have this theorem about invariant. So for toric, maybe you need to check only toric blobs, right?
Yes, I think so.
if boundary is toric, then
Yeah, sure.
And the question, small question. So in the case when it's not a premise table, not a body table, did you check, for example, automorphism group of a pair? Maybe it's not reduction.
Yes, this is a
Out of curiosity.
good question. So actually, now we have a classification. We can compute automorphism groups for all the pairs. We can check whether they are reductive or not, and reductive is a necessary condition for key stability. So I have not checked this, but maybe it is an interesting thing to do, just to compute the automorphism groups in all these cases.
How this abstraction works. Of course, beta is stronger. But just out of curiosity.
Yeah, it is a good thing to do, but I have not done this.
Any more questions? If not, let's thank Kostya again.